Hello, and welcome to another one of Ethan's engineering videos. Today we're going to be talking about Cartesian heat diffusion, which is to say we're going to take an imaginary sample volume of some substance, pour heat in, a heat flow, in from all of the three directions. Cartesian means a three-directional linear 3D space. So we're going to pull it in from all three x, y, and z directions, and then we're also going to take into consideration any heat that's generated within the function and any heat that is stored inside the function. And of course, any heat stored inside our sample volume will change the temperature, and so this will help us model how temperature changes over time relative to all of the heat coming in and going out of our sample volume. So to get started, obviously I'm going to need to draw our sample volume, so I'm going to just make that a cube, and we can get right on our way. So we're going to start by drawing our cube here. We're going to make it pretty big so that it's of an adequate size. A bit too diagonally far, but you know, don't crucify me, please. That is a really wonky looking cube. Wow. Okay, everything up to this corner looked fine, I guess. Let's try this again. You go down. That's a bit better. I mean, it's still ugly, but it's tolerable. So anyway, we're going to label our axes now. So I'm going to draw. These are going to be all the positive directions. We're going to have up being positive for y, this way is going to be positive for x, and into the blackboard is going to be positive for z. I'm going to also draw the center of our cube here just to help you get a little reference. This is floating right in the center of our cube, so try not to get yourself lost in the perspective of my mediocre cube drawing. So I'm also going to label the sides right here. So this is going to be our side dx, this is going to be our side dz, and this is going to be our height over here, I suppose, is going to be our dy. So as you can see, we have our three sizes right there. And so now we're going to worry about our heat flows. So we're going to have heat flowing in to this sample volume from all sides. So we're going to have it coming in this way. We're going to call this qx. And it's going to be leaving in the positive qx direction, or positive x direction as qx plus dx. So again, this tells us its position. This is position x. This is position x plus dx. So it's only moved through our sample volume. And we're going to do that for the other directions as well. Going in, we're going to have qy, and leaving out the top, we're going to have qy plus dy. And then going into the blackboard, we're going to have qz, and going out the back of the blackboard, we're going to have qz plus dz. Clearly, I don't use the letter Q enough in my daily life that saying Q over and over again is starting to mess up my head. So what exactly is qx plus dx and qx? How do those heat flows work? Well, we're going to assume that they are linearly related. We're going to kind of decompose them. So we're going to say, and this is going to go for all three of our different directions, we're going to say that qx plus dx is approximately the same as taking our regular qx, like what's going in, and adding to it the derivative, however that heat flow changes over direction, multiplied by our dx. So we're going to call it dqx over dx multiplied by dx. So obviously this looks a little funky, but this is a derivative. This is how our heat flow changes as we increment across its axis, and then this is how much we've incremented across our axis. So I'm going to rewrite this 2 more times just to make sure it's really clear, because this is really important. qy plus dy is approximately equal to qy plus dqy over dy multiplied by dy. And then same thing for q of z plus dz is approximately equal to q of z plus dq of z over dz multiplied by dz. Now again, you have to make the distinction that this is a length, some infinitesimally small length of dx, and this is the derivative in the dx in the x direction. So yes, these would, the way we've written it, these would cancel, and so it would be q plus our dq of x. That does make sense if you think about it. If we're moving an infinitesimally small amount away from our starting point, we should be adding an infinitesimally small amount of heat to our qx. But we're going to leave it like this is now because they're not quite the same, and we're going to be doing substitutions later on, and so the writing it this way is neat. So just take my word for it, all right? And then as far as the other two quantities I said we were going to look at, we're going to be looking at energy stored in our cube, which is obviously going to be the net amount, like the net change of our energy of our system, because any energy that isn't coming in, going out, or being generated obviously must be staying within this volume because it's not coming in or leaving, so it has to be still in there. So we're going to take a look at both of those. Clean this up a little bit. There we go. So I think I've written both of them down here. Our energy generated is pretty simple. This is something that we're just going to like create. We're going to assume that we are given some sort of energy generated per unit volume, some kind of watt per meter cubed figure. So we're going to call that Q dot. So that represents, I'm just going to put in little brackets here, watts per meter cubed. And we're going to multiply that by the volume, because again, this is heat generated per volume. So we're going to need, not heat generated, this is heat energy generated per volume, multiplied by the volume, which is going to be dx times dy times dz. Very simple. It's a bit more complicated, however. I don't know why I started drawing a summation. Still got computational methods homework on my mind, I guess. Some of the chalk just out of the way there. And the final thing we're going to be looking at is our energy stored. Right? As I said before, this is going to be our connection between the energy in our sample volume and the temperature of the sample volume at, in that area. So how do we do that? Well, again, we're looking at this sample volume, so we can be pretty confident we're going to need our dx, our dy, and our dz. And of course, as I said, this is our link to the temperature of our sample volume, so we know that our change in temperature over time is going to be in there as well. But obviously, there's some other stuff that's going to make these two things connected to each other, and how are we going to bridge that gap? So when we're talking about the energy being stored in a volume, and how that relates to temperature, we know that different substances have different heat capacities. Specifically, how their heat changes based on temperature increments. So how much energy does it take to increment a certain amount of this substance by a single degree? And that's going to be our heat capacity. So I'm going to call that capital C, I think it's V because it's constant volume heat capacity. So that's I'm just going to put the units in brackets down here, really small, you might not even be able to see them. That tells us the change in joules over, for a specific amount, which is measured in kilograms per degree Kelvin. So per kilogram of substance and per degree of Kelvin, this is how much energy is going to be needed to like make that kilogram, that Kelvin increment in temperature go. So since again this is Kelvin per time, those kelvins cancel out. So now we have joules per time, which is a watt. So right now we have it in watts per kilogram. So how do we get that into volume? Because again, I said we only know the volume of substance. We don't actually know the kilograms, the actual mass of the substance we're looking at. So what we're going to do is we are going to set this equal. We're just going to put the density in there because our density tells us kilograms per meters cubed. So those kilograms will cancel out down there. This is, I'll just put this down here. This is kelvins per second, just to show you the units cancel. Our kelvins cancel. So we have joules per second, which is a watt per meter cubed. Then right here we have the volume, so these will cancel out with the meters. And so all of our units will work and we'll end up with watts, right? We'll end up with joules per second. So these are all the things we need to know about our system, kind of laid out flatly. And so now we'll get into the actual kind of more messy derivation. So the fundamental part of this cube, I don't know why I did that. I have chalk on my hands and there's a handprint on the wall, so don't worry about it. The principle for this entire thing is energy conservation, right? We know that energy in minus energy out plus any energy generated must be equal to the energy being stored, right? Anything coming in and then anything being generated within there, so coming into existence already inside, minus anything that's leaving, anything that doesn't leave must still be in there. That's kind of, again, common sense, definitional. Everything that doesn't leave must still be contained and must be stored, and any energy stored will increase our temperature. So now I'm just going to take all of this stuff we've worked up down here and throw it up on the board, and it's going to be probably pretty long, so I might have to double stack it, but we'll see. So what's coming in? Well, that's going to be our Qx, our Qy, and our Qz. And what's going out is going to be our Qx plus dx. And obviously that's going to be negative because E out is negative, E in is positive. But instead of writing it out, both of those out entirely, since we've already explained the linear approximation we're using, where qx dx is equal to qx plus this term right here. Our qx, because again, if you think about it, this is negative, so I'll write it over here on the side really quickly. So qx would be added positive, so positive would be minus qx minus dqx over dx times dx. So as you can see there, these two cancel. So we don't actually need to write as much as I thought we did, because I'm just going to do that. You're just going to have to acknowledge the fact that when we do our E in minus our E out, our QX's and the QX going into the actual thing are going to cancel. So we're going to only be left with these right here. So I'm going to put these in parentheses right here, just to notate that we're going to take care of that ahead of time. So doing our E ins minus our E outs is just going to give us negative dQx. That looks more like a D. That doesn't really look like a Q. So we have dQx over dx multiplied by dx. That's going to be negative minus d of qy over dy multiplied by dy minus d of qz over dz multiplied by dz. Then we're going to add our energy generated, which is going to be plus q dot multiplied by dx, dy, dz. That's our control volume. And that's going to be equal to our EST. I'm just going to leave that as energy storage for now, because we're going to have to do a little bit more cleaning first. In fact, I could probably leave our q dot as energy generated for right now. Yes, now that I think about it. So I'll just leave plus EG is equal to EST. To save us a little bit of space, because we're probably going to need 2 more columns. Maybe, depending on how big I write. So you'll notice here that we have something that doesn't really make a lot of sense. And the reason for that is because even though we've canceled out our original QX, we still have a QX in there, but now it's in a derivative. So what do we do with that? Well, this is the part where we need to use some stuff we've learned previously about defining heat flows, and specifically heat flows per unit area, and how those translate to our, our heat transfer coefficients. I'm trying to remember what the exact wording is for, but it's eluding me, but I'm not going to get hung up on it. It's our value we use K to represent it. It's a direct representation of how a movement in a linear direction affects our heat transfer. So we know that, for example, Q of x, again, is the same thing, since this is a heat flow, is the same thing as a heat flow per unit area in direction x multiplied by the area. And so we can calculate this because, again, we know the definition that Q area Fx is going to be equal to negative K multiplied by dt over dx, right there. Right? That's what I was saying, where heat per unit area is equal to the negative, because again, heat flows from high to low, so opposite of the temperature differential. And again, this K right here is just what describes a specific substance's heat transfer capacity. Not heat transfer capacity, just heat transference, I suppose. So we have dt over dx, and then of course our area is just going to be the area that it's moving through, right? So our qx right here is going in our x direction, which means the area it's moving through is our dy by our dz area on that side of a cube. So it's going to be times dy times dz. Now I'm just going to put a little box around this. So that's kind of a first big thing you need to know coming in to do this derivation, is that we can decompose our dq of x, or q of x into this. So now what we're going to do is we're just going to take the derivative of this with respect to dx. So we're just going to have that here. So we're going to have negative d over dx. And again, we're going to take this right here. So what is in terms of d of x? So we have negative k, which, who knows how k changes with volume, so I'll leave that in there. So negative k dt over dx, close the parentheses, because dy and dz are the only other things trapped inside of this derivative right here. And we know that obviously those are just units of length, right? There's some infinitesimally small unit of length, so they can be pulled out of our fraction. They don't have anything to do with it. Like the changing in the direction of x doesn't change the area of our square because they're all constant, right? Qy and dy and dz don't change as we move along x, so we can pull those out. And since we already have our dx volume here, our dx is already outside of our derivative, you now have dy and dz. So now we have all three, the whole unit volume. So if we do the same thing for each of these as well, for qy and qz, the exact same thing will happen, except for we will have different derivatives on the outside. So we'll have d over dy of negative k dt over dy multiplied by dx dy dz. And then I'm going to wrap around here and say minus d over dz of negative k dt over dz multiplied by dx dy dz. And now this is where I'm going to write in our E of g right here. So plus E of g. Well, E of g is just our q flow times dx dy dz. That's going to be equal to our energy storage, which I can write in as well. It's going to be rho cv dt over dt multiplied by dx dy and dz. And now if you look at this, if you have any remaining brain cells, you might notice that dx, dy, and dz are a component of every single term in this equation. So we can simply just divide out by our sample volume right here. So we can just kind of get rid of all of it, and we don't need to worry about it at all. So when we do that, we get a much nicer equation right here. So we have, I'm going to put this out front because it's positive, so we have Q dot, which again is our heat generation per unit volume, minus I'm going to pull the negative outside of this derivative so that they're all going to become positive. So plus d over dx. I guess I'll go x first. Okay, actually, we can also just do this derivative anyway. So we'll do that while we're here. So if we look at this, we're changing with over a specific area of x for both k and dt over dx. So our change in temperature over our length, and then we're looking at how that changes with respect to length. And same thing for k. How does our change in thermal conductivity change with respect to moving in x? And obviously, we don't know, because there's no guarantee that either of these two are constant, so we can just take the derivative of them with respect to x. So we're going to do that. We do trying to remember if we did the product rule here. I feel like we do, but I'm going to assume no. So I'm just going to take the derivative of both of these with respect to d of x. So dk over dx, and then d squared t over dx squared, plus, do the same thing for y, dk dy times d squared t over dy squared, plus dk dz times d squared t over dz squared, and then we already have the q, is going to be equal to, this is just rho cv dt over dt. So this is significantly more simple than what we started with. So thank goodness for that. However, my knees are starting to hurt, and they're getting a bunch of hair and chalk dust on them, which is not so simple or so great. But you know what? We're going to work with it anyway. So looking at this, we can now more or less make some assumptions about this. So for the sake of our class, we talked about how we're going to assume that K is constant everywhere. And so what that means. I'm trying to think. I think I was supposed to do the product rule here. Now that I'm really looking at it and trying to move on. 1 second, let me just double check this in my head. Might take me a moment, but I'm definitely thinking. Yeah, we were supposed to do the product rule, so I'm going to do that really quickly. So I'm still pulling the negative out ahead of time, so it's just, I'll just make these both positive, these both positive, these both positive to make it easier. So we're going to do product rule, so G and F prime, so it's going to be D and then derivative of K, so this is going to be not squared right here, and these are going to be squared, and I'm just going to write it below to make the room. So it's going to be this underivized and this, and then we're also going to do plus, so G F prime, so F G prime. So we're going to have K times D squared T over dx squared plus D, or plus K D squared T over dy squared plus K, that was a horrific K, wow, that's really awful, plus K times D squared T over dz squared, right there. So these are our two terms. So this is GF prime, so not the derivative, and then not derivative. So right here is everything. So this is the whole equation. Q, which is our EG, all of these, which is kind of the result of our in and out flows, and all of that must be equal to what's being stored. So this is kind of, this technically is, I'm going to put a big square on it, this is the tried and true Cartesian heat diffusion equation, right? This accounts for any heat generated inside or outside, not outside, any heat generated outside, any heat coming in, or I guess the net flow of heat in and out. And all that depends on the change in temperature across our area in each of the directions, as well as the change in heat diffusivity across all of our directions, and all that is equal to the change in temperature of the overall volume over time. So this is kind of the true thing, but for the sake of our class, we're going to make some pretty big assumptions. So we're going to say, first of all, if Q dot is 0. So we're just going to assume that we're not actually generating any heat, which just means that that term is gone, right? More or less, it's fine. The other thing we're going to do is we're going to add another and right here. So and K is constant. So what does it mean if K is constant? Well, that means that the derivative of K is equal to 0. dk, let's say dk is equal to 0. And you notice I didn't use the bottom of a fraction because constant implies that it's constant across all axes. So dk with respect to the x direction, the y direction, the z direction, all of it, we're assuming our material is homogeneous heat diffusivity wise. So what does that mean? Well, that means the first term I wrote up here, dk over dx, that's equal to 0. So this term becomes 0, this term becomes 0, this term becomes 0. So all we're left is the bottom ones. And this, of course, is also 0. So factoring those in, we're going to get, this whole top row is going to be equal to 0. So we're only going to have what's left on the bottom. We're going to be left with k, and I'm just going to factor it out because we can. It's present for all of them. Is equal to d squared t over dx squared plus d squared t over dy squared plus d squared t over dz squared. And all of that is equal to rho cv dt over dt. But we're not quite done. And that's because since k is a constant, if we just divide everything and put it right on over here, we can use that other special value we found way earlier, a couple days prior to going over this problem, alpha. And since alpha, I'll just put it over here on the side real quick. Alpha is equal to k over density constant volume heat capacity. This actually just becomes, when you divide by k, 1 over alpha. So we can rewrite this without the parentheses now. I'll try to make it really nice and fancy looking just for you. So d squared t over dx squared plus d squared t over dy squared plus d squared t over dz squared. It's going to be equal to 1 over alpha. I don't know if that's a super perfect alpha. We're going to go with it. dt over dt. And this right here is, for the sake of our class, what we're going to use for the Cartesian heat diffusion. So that right there is our answer. Very, very nice and pretty. And then right over here, we have the more generalist, kind of truer answer, which again incorporates all of the stuff that we're just kind of assuming out of existence for the sake of our class, because it's relatively early on in our engineering and heat dynamics education. So we're not going to worry about generation and a changing thermal conductivity throughout our substance. We're just going to assume that we can get rid of about 4 out of those, 4 plus 7, 8. So we're going to get rid of half of the terms in this equation by just assuming they're not real. And so we'll get our final answer that you can very clearly see over here. But again, true answer, answer for the sake of our class. But no matter which answer you do prefer, I thank you for watching. I really appreciate your time and your viewing attention. So thank you, and have a good evening.